Okay, so it's on time now, and welcome everyone to this session. I'm Lin Lu from Shandong University, and I'm in China now. So this session, we have two papers on fabrication. And the first paper is about computational design of generalized centrifugal puzzles. And the authors are Nakio and Takifumi Zato from Tokyo University of Agriculture and Technology. I have set Naoki as the co-host, so you can share your screen now. Can you open your video and share your screen?
Okay.
Yeah, it's smooth on my side. So are you ready to start? Okay, so welcome, please.
Okay, so let me present our work, computational design of generalized centrifugal puzzles. I'm Naoki Kita from Tokyo University of Agriculture and Technology. So first of all, I'd like to ask you that, can you unlock this puzzle? The puzzle is composed of two identical parts. So the answer is spin the puzzle. Sorry for the spoil, but it is necessary for our presentation. So solving this type of puzzles requires exploiting gravity or centrifugal force. Then when the puzzle is spun, the centrifugal force is equally applied to the internal locking mechanism. In this case, the sticks, and these sticks are pushed away to the outer side. As the result, the puzzle is unlocked and disassembled to two parts. We can find such type of puzzles in the early 20th century. And then several puzzles that exploit centrifugal force have been invented. As shown, we can see that those existing centrifugal puzzles have simple mechanism, and the puzzle shape is also simple. So in this work, we focus on generalizing centrifugal puzzles. We propose a computational design method to generalize centrifugal puzzles. With our method, we can create centrifugal puzzles with more complex shapes. So, given a target 3D model, a user can configure the pose and core position. Here, the core is the puzzle mechanism, shown in the yellow box. And then our method optimizes the core position and size. To rotate the puzzle model stably, we also generate a support structure. Without the support structure, solving the puzzle is very hard. So the support structure is regarded as a key to unlock the puzzle. To summarize our contributions, we generalize the traditional centrifugal puzzle. We also generate support structures such that we can solve the puzzle stably. And we demonstrate the result by printing several models and conduct physical validation. In the computer graphics community, researchers attempt to extend the traditional geometric puzzle. The traditional polyomino puzzle is a tiling puzzle on 2D plane. Rowe et al. Extend it to the surface of 3D models. The 6-piece bar puzzle is a type of interlocking puzzles, which have simple geometric shapes. Spin et al. Generalized it to arbitrary 3D shapes by embedding the core mechanism to the 3D models. Similarly, Sun and Chen generalized Rubik's Cube to more complex shapes. The computer graphics community also pays an intensive attention to computational design method. Make It Stand optimizes the standability of 3D models. Spin It optimizes spinability of 3D models. And Jacobson proposes a method to create generalized matryoshka, a Russian nesting doll. So regarding this point of view, we can say our method optimizes the unlockability. Here, locking mechanism should be unlocked stably without accidental unlocking and eccentricity during spin. From observations of the traditional centrifugal puzzles, we first consider several design constraints. Also, we parameterize core mechanism of the centrifugal puzzle. Based on the design constraints, we embedded the core into a given 3D model and optimized the core design. To generalize centrifugal puzzles, we consider 3 design constraints. First, the core should be embedded in a given 3D model without collision. Second, the rotation axis of the core should go through the center of mass of the model. So this value satisfies the 2 constraints, but the core is too small to generate a core mechanism. So it's not good. And so in addition, if the core is too small, it will cause an accidental unlocking because of the 3D printing precision issues. Therefore, third, the core should be as large as possible. So we optimize the core position and size that satisfy all these constraints as the one shown on the right panel. Next, we parameterize puzzle core mechanism. The one shown on the left is the cross core employed in the traditional centrifugal puzzle. Additionally, we design the cylindrical core shown on the right. The cylindrical core allows us to access the internal compartment through the hole. Now we can formulate our design problem as a maximization problem. The first design constraint is used as a hard constraint. The second design constraint is not explicitly used in our optimization because we design our user interface such that rotation axis always pass through the center of mass of the model. The third design constraint is now our objective function. So we maximize the core volume subject to collision-free core embedding. We solve this optimization problem by employing particle swarm optimization. Next, we would like to explain the support structure. When solving our generalized centrifugal puzzles, we have to keep the model in a valid position. So that's why we need a support structure. We first generate a cylindrical support structure. But here, you can see that when we remove the model from the support, the forefoot and tail of the puzzle model are obstructed by the support in the configuration shown on the slide. here. To address this issue, we sweep the puzzle model to the removable direction to generate a swept model. Then subtract the swept model from a cylinder to generate a support structure. Although we can put the puzzle model on the support and keep it in a valid position, the center of mass is no longer aligned with the spinning center of the puzzle model. This is because in the former optimization, we optimize the puzzle model such that the center of mass of the model and the spinning center of the core are aligned. But if we put the puzzle model on the support, we have to take into account the total center of mass of both puzzle and support model. To address this issue, we optimize the mass distribution of the support model. So we first voxelize the support structure and slice it in a bunch of slice images. Then we apply the iterative semicircular top layer removable procedure. In this procedure, we attempt to align the center of mass to the spinning center. So we calculate the bisector of the support and remove the boxes of the blue colored boxes. So iterating these removable steps, the center of mass is gradually moved to the spinning center. Finally, we subtract the boxes from the support model to generate the support model with optimized mass distribution. So we show several 3D printed results. In the first row, we embedded the cross core in the spot model. In the second row, we embedded a cylindrical core in the bumpy cube. So we can put something secret inside the cube. In the third row, we embedded 2 cores in a single model. In this case, we have to unlock these cores in a certain order. So my first attempt failed. I have had to use this larger support first and unlock the first lock. Then we can unlock the second lock. Yeah, this is interesting application of our method. So conclusion, we have proposed a computational design method to generalize traditional centrifugal puzzles. Using our method, users can create their unique centrifugal puzzles with arbitrary 3D shapes. There are several future works. First, we partition a target model with a plane, a parting plane, but it does not have to be a plane. Taking into account the puzzle appearance and the aesthetics, a parting surface would be better. Also, camouflaging the parting surfaces is important to avoid providing any clues to the solvers. Finally, in this work, we parameterize the two core designs, but it would be interesting to use other core designs. So that's all. Thank you for your attention.
Thank you, Nike. It's a good presentation and really interesting work. And for the audience, please raise your question in the chat window. And I noticed there are already 2 questions. Okay, can you see the questions in the chat window yourself, Naoki?
Yeah.
Yeah, so the first question is from Martin, and it seems to me that the pot structure basically give away how to spin the object. Yeah, that's also okay. So would you please please.
Yeah, maybe yeah, our puzzle need extra jigs we provide as a support structure, but if you can see the slide and this low point tree, the support structure is the part of the puzzle itself. So we can say that this is the self-contained puzzle, so which is we can say puzzle. So I think we can include the support structure in the puzzle. So yeah.
Yeah, can we say that if without the support structure and it would be a very hard puzzle? Or is there any evaluation to evaluate how difficult of the puzzle? It's interesting. it's really interesting direction to.
Actually,
as you know, you use it as a secret holder for your key.
Your key. Actually, I couldn't unlock without support structure. Yeah, it's very difficult without support structure. So.
We can see several questions. Maybe the second one from Algae.
Fabrication process is a core model, so 3D printed or fabricated.
Yeah.
Yeah. I 3D printed all the parts, core and the outer model, and we did not consider the friction property. So I adjust the clearance offset slightly by when using our FDM 3D printer.
Yeah, no problem. You fabricate both the out shape of the puzzle and the core, right?
Yeah.
Okay. Maybe we move to the next one. Can you extend your approach to different types of puzzles? Okay, this is from George, from Professor George.
Sorry, I don't know the example about color statue, but I think our approach can extend the other puzzles with employing gravity or external forces.
Yeah, I'm sorry that for me, I either do not know this statue. Yeah, maybe we need to check offline. Okay, we will have 2 more questions. Yeah.
It's confident to see applications of your method outside of puzzles. Yeah, I think our method can apply to the physical security because we can put something secret inside the boxes. So this is not, I think this is not a toy problem like puzzles, but our method can apply to the security or the architecture.
Okay. We have next. Oh, thank you, Jacqueline. Thank you. Yeah. And there is another question from Tim.
Yeah, maybe you can make it by having multiple copies in services that the user don't know how to put.
Yeah, this is good question. Yeah, interesting.
Yeah. So maybe change the cutting frames. This is not revealed in yeah. I think it's yeah.
It's actually suggestions.
Yeah, thank you very much. Yeah.
Okay. Okay, I noticed that you have showed the project page or your contact information in the last page, right? And also we can find all the talk online. So maybe we can, if we have further questions or remarks or comments, we can discuss further. Okay, so yeah, thank you, Naoki, thank you.
Thank you very much.
Thank you, and thank you for all the audience. Yeah. So next, we move to the second talk in this session, and the second talk is about ceramic 3D printed sweeping services. And actually, I'm one of the I'm the co-author, and the first author is Fan Chaozhong from Shandong University, and he's an undergraduate student. And yeah, I take this privilege to say more about him because this is the first time for him to attend these international conferences. Yeah, and now he's only year 3 undergraduate student. So yeah, okay. So Fan Chao, would you share your screen? Okay. Can you hear me? Yeah, please share your screen. And if you want, you can open your. Yeah, okay. Yeah, you have the video.
Hello everyone. The light is weak. I'm sorry.
We cannot see your screen.
Oh, okay.
Okay, so please.
My name is Fan Chaozhong from Shandong University. I am undergraduate student now. It's my pleasure to present our work, ceramic 3D printed sweeping surfaces. And our collaborators are from School of Computer Science and School of Mechanical Engineering. And my supervisor is Lu. These days, we can see that desktop ceramic 3D printer gets more and more popular for designers, artists, and makers. As a highly viscous pseudoplastic liquid, the printing material clay produces featured aesthetics, as we can see it in the picture. However, the module design process is complex and unfriendly to people without modeling experience, and no modeling tool customized for plain 3D printing. In addition, there are special constraints. Firstly, too large inclination would cause module cannot support itself and collapse. And because of the viscosity of clay, if the printing path is discontinuous, moving the print head without extruding will thus pull on the structure and induce unwanted deformations that amplified over time and eventually lead to failure. So our goal is to propose a modeling tool for ceramic 3D printing. It's designed for ordinary users to make ceramic 3D printing more easily. And the tool integrates the ceramic printing constraints, includes self-supporting, non-self-intersection, and collision-free. And then generate the printing file, namely G-code, with the guarantee that the extruder traces a single continuous path without stops. During the fabrication, our continuous paths avoid the potential collision between the printing head and the physical model. Again, et al. Proposed a method for integrate tool path planning and support structure generation. The work guarantees a single continuous printing path for the entire model. But the support structure needs to be manually removed later. Fuller et al. Proposed a method of forming shells by sweeping with a curve. The input is simple, but the generated models are rather limited. Takahashi et al. Explored the combination of the height position of the extruder and the amount of extruded material to enhance the capability of FDM. And here is basic pipeline for our framework. Input of work is 3 curves joined with B-spline or predefined line as CS, CT, and 5 curves shown in figure. The user completes the join of the 3 curves on a 2-dimensional plane. After that, a model conforms printing constraints is automatically generated. And then a single continuous path generated and stored in a file, format of which is G-code. And finally, use a 3D printer to fabricate. I will introduce the last 3 phases specifically. First, I will introduce sweeping surface modeling and the problems need to be solved. The canvas used to draw CS and CT is correspondent to a plane across the CSs in what coordinate. The canvas used to draw phi is correspondent to XOY plane. As you can see, the CS is located at the starting position of phi. The CT is located at the end position. And the average transition curve is obtained by interpolation located at one of the points on phi. In the figure, each blue vertical line represents a transition curve. We sample uniformly on CS and CT. The number of samples is the same, forming a one-to-one corresponding relationship. Similarly, with sampling on phi, afterwards we get an intermediate point on each transition curve by interpolation. The lowest point of each transition curve overlap with a point on phi. Then we have the point cloud for the entire model. All the adjustments are for this discrete point. As we said before, the transition curve is obtained by interpolation, so we provide a control curve for users to edit the interpolation function to have more freedom on the surface shape. It's actually a cubic spline with natural boundary. However, there are potential problems to be aware of. Firstly, in the absence of support structure, part of the slope angle too large are likely to collapse. And secondly, even if there is no self-intersection on phi, a generated model may exist. These are all problems that we need to solve. In order to solve the first problem mentioned just now, we need to detect the model and locally modify the part whose slope angle exists the overhang threshold, so that achieve self-support. In our experiment, the threshold is 15.7 degrees. The acquisition of this value will be stated later. Specifically, we traverse the sample point along the axis. For each sample point, if its slope angle is larger than the threshold, we compute the new position of the sample point. Let's satisfy the threshold and then drag it to there. Then we apply the same translation to the following point on the curve. During the process of sweeping, collision may occur between the transition curve, leading to self-intersection of the model. When a straight line connecting 2 points on phi is close to the center point O, like the green line in the picture, the two transition curves located at these 2 points may collide. So it's the next problem we need to solve. We traverse any 2 points on phi, and if the straight line connecting them is close to the center point O, we apply further check for their transition curves. If the distance between two intermediate points on the transition curve is approximately 0, the sweeping surface is self-intersected. Then we compress CS and CT to eliminate self-intersection. By the way, we operate on point and don't need to compute the function of the curves. In the next stage, we generate a G-code file that records the printing path and the amount of extrusion. First of all, we should pay attention to 2 things. The first is to keep the printing path continuous. And the second is to deal with the possible collision between extrusion head and the printed model. The 2 pictures on the left shows the collapse caused by discontinuous printing path. For the second problem, we will make a specific statement later. The third picture shows the collision between extrusion head and the printed model. As mentioned before, we generate a single path to ensure that the printing process is continuous without interruption. However, if always use this path generation algorithm, there is potential collision as mentioned before. Assume that the height of the extrusion head is h. The height difference between CS and CT is greater than h. When the highest point of CS is printed, the second highest point of CT has been printed, and their height difference exists h, then collision will occur. Therefore, we improve the path generation algorithm and call it adaptive zigzag path algorithm. The image on the right shows the printed model by the path generated using the new algorithm. We divide the model into 2 parts. They are shown in blue and red. For the red part, we use the sampling method mentioned before and generate zigzag tour path, shown as the green printing path in figure. For the blue part, we calculate CS's value of returning point. For every value, we look up the highest point of every transition curve, which has the nearest distance with it as the returning point, such as the purple point in figure, and generate the zigzag tour path as the yellow path shown in figure. In this way, we guarantee that the extrusion head will not collide with the model when it moves. Too much extrusion amount goes on controlled surface quality, waste of materials, and more fabrication time, and thus uncertainty. But if extrusion amount is insufficient, the overlap area between the layers will be too small and cause the module collapse, like the left picture. Therefore, we propose the adaptive extrusion amount computation to get the appropriate value. The optimized result is shown in the right picture. In the algorithm, we keep the position of the sampling point unchanged and adjust the amount of extrusion simply by changing the line width. We traverse every printing point from the bottom layer to the top layer and keep the line width of the current point and previous point of the neighboring layer equal, where expanding or reducing their width simultaneously with the same scale until the proportion of overlap reach 2 divided by 3. Based on the range of parameters, we can deduce that the threshold we used before is 15.7 degrees. Finally, here are some printed results. we invite 10 undergraduate students to perform the surface design. It takes 2 to 10 minutes for them to finish designing the CS, CT, and PHY. And we pick some samples from the user-created surfaces and fabricated them with our 2 desktop 3D printers. The screen shows 3 printing results of the first 3D printer. These are other 3 printing results of another 3D printer. And we filed the models to make them more rigid. In fact, more than just desktop printing, we can apply our framework to large-scale model printing, and some materials with similar properties to clay can also be used, such as cement. The picture shows the chair we fabricated with cement. To demonstrate the printing process, we shot a video. First, we drove a snail using our framework. And then fabricated with our desktop 3D printer. We can see that the shell is thicker than the head. The fabrication process takes about 7 minutes. In conclusion, we have proposed a framework for user interactive sweeping surface modeling, integrate the ceramic printing constraints like self-supporting, without self-intersection, and collision-free, and generate a single continuous printing path. We improve on the range of models that can be printed in clay, and the printing process is reliable. The first limitation is that we didn't do stress analysis for the models. For example, the wings of the pigeon in the picture are easily broken. Second, the shapes that can be formed by sweeping are limited. We are going to try more curves. You can get more information from our project pages. Thank you very much.
Okay, thank you. Congratulations for your first talk on the international conference. Thank you. Yeah. Okay, so we already have questions from in the chat box, okay. And there are Jacqueline, you. I heard anyone want to raise the question? Okay, you can also raise the question in the chat box. And the first one is from Algae, and the question is: can this work be extended to from your extrusion-like models to more generic shape, providing that the shape that has infill and with one continuous path? Yeah. Actually, this is a very, very good question. Yeah. So you have anything you want to say something?
Let me think.
You can
Okay. Actually, we didn't feel it. We just generate a surface. Hello? Can you hear me?
Three.
Sorry, I can't hear you. Hmm? Yes.